We are continuing with the Test 2 practice problems, going through them. We're on number 17. So we have a 5.0 kilogram object is pulled to the west with a force of 3.6 newtons and simultaneously pushed in a northeast direction, 45 degrees, with a force of 2.8 newtons. What is the magnitude and direction of its acceleration? So I can make a free body diagram. We have a westerly force of 3.6 newtons. I'll call that Fw. And we have a northeast one, which I'll write, that'll be Fne. That's 2.8 newtons, and that is 45 degrees. Okay, so we're looking for the acceleration. So this is a very straightforward F equals ma type problem, because we can get the net force and then we can get the acceleration. So we can put on a coordinate system. We can break down Fne into its horizontal and vertical components. So that and that. Whoops. Yeah. So So the horizontal part is the cosine. So that's Fne cosine theta, cosine of 45 degrees. And this right here will be Fne sine 45 degrees, breaking that up into components. So in the horizontal direction, we have Fne cosine 45 minus Fw will be the mass times the horizontal acceleration. And vertically, we only have Fne sine 45 degrees equaling mass times Ay. Okay, so yeah, I have all these numbers here, and I have the mass 5 kilograms, so all of this divided by 5 will give me Ax. Because I have limited space here, I will just write the final answer there, but yeah, it's just dividing by m. So we will have 2.8 times the cosine of 45 degrees minus 3.6, and that all gets divided by 5, and that gives me negative 0.324. Okay, and Ay, I have all of this, and I'm going to divide by m. So this will be 2.8 times sine of 45 divided by 5, giving me 0.40. Sorry, these are both meters per second squared. Okay, so my acceleration in components is this. It's negative 0.32 to the left and then 0.40 upward, so like this. That would be going this way. That kind of makes sense. If you add this vector to this vector, it kind of be pointing in that direction. Okay, so again, this is 3.2, this is 4.0. So the magnitude of the acceleration will be the square root of this squared plus this squared. Again, just in the interest of space, I'll just write the answer. So I'm doing the 0.32 squared plus the 0.40 squared, and I'm getting like 0.51 meters per second squared. And the direction, if we call that theta, that'll be the inverse tan of 0.40 divided by 0.32. Inverse tan of 0.40 divided by 0.32 is 51 degrees. Okay, so that's the magnitude of the acceleration, that's the direction of the acceleration. Part B, if the object was initially at rest, how long will it take for it to travel 4.0 meters? So this is, even though it was 2D to begin with, if the object starts at rest and then accelerates in this direction, it will just stay along that line. So it's really a 1D problem now in terms of just its motion. This is one-dimensional motion, and not only that, but assuming these forces are all constant, which we can assume they are, we're not told that they change at all, that means the acceleration that we just found in part A is constant. So this is a constant acceleration problem. So we have all our usual quantities. We have the acceleration of 0.51. We can assume it starts at, we can call that 0 where it starts, and we know that we want it to travel 4 meters, and we want to know what the, oh, and we know it starts at rest, and we want to know how long that takes. So we go to our constant acceleration for our 4 constant acceleration equations. We pick the one that does not include VF, and I think that one is this one. I can put a 0 in there and put a 0 in there. So xf is 1/2 at squared. And I can solve for t. Multiply the 2, divide by the a, and that leaves t squared, so take the square root. And plug everything in. So the square root of 2 times 4.0 divided by 0.51. Go to my calculator. 2 times 4 divided by 0.51. And I'm getting, well, to 2 significant figures, 4.0. 4.0 seconds. So that's how long it'll take to go 4.0 meters. Okay, so that's 17. A 35-kilogram object initially at rest sits on a table. A rope attached to the object pulls straight up with a force of 220 newtons. Does the object move, and if so, what is the acceleration? And then we want to know what the normal force is. Okay. So let's draw the situation. We have the object is sitting on a table, so we have gravity pulling downward. We have the tension of the rope pulling upward. We also have the normal force pushing upward. Right. So this is a one-dimensional problem. Nothing at all is going on horizontally. So we have the normal force plus the tension minus gravity equals mass times acceleration. Now gravity is mass times little g. Okay. So now we don't know tension and we don't know the normal force. So it seems like we have 2 unknowns here. However, whenever you do a does an object move kind of problem, typically the approach is let's assume it doesn't move and see if everything makes sense. So if this were 0, right? If this were 0, then this would all have to add up to 0. And of course the way normal force works is the normal force is whatever it needs to be to make up to make this equal 0. Right? By the way, if this object were moving, if it went up, then normal force would be 0 because it wouldn't be touching anymore. Okay, so but if it were 0, what would normal force be? And does that all work out? So the tension is 220 newtons, and m times g, so that's 35 kilograms times 9.80, And if I put that into my calculator, I get 343 newtons. So, right, so 343 newtons downward. The rope is only pulling up with 220 newtons. So the table must be doing some work just to even that out. And by the way, the answer is then the object is not moving. Because again, if the object were moving, this would be 0, because the normal force, it wouldn't come into play because the object would be going up. But we see that can't be the case because gravity is stronger than the rope, right? The only way this could be going up is if the rope were more than gravity, and it's not. Right, so it's not moving. And then we can now finish part B actually right in here, because we can figure out, so this is 0 because there's no acceleration. We can figure out what the normal force is. So 220 minus 343 is negative 123. So we can see that the normal force is 123 newtons. The answer to part B. See, if we had gotten that 220, if the weight, the mg, were less than 220, right, then the tension would already be more than gravity. So there would be nothing for the normal force to do. It would be 0, and then we would have excess force going upward, and so we would not have a 0 acceleration, and so it would have gone up. But because the weight was more than 220, the pulling force of the rope, it doesn't move, and there is some normal force to make up the difference. All right. 19. A 1.35 kilogram object is sliding to the right on a surface at an initial speed of 10 meters per second. The coefficient of static friction is 0.752, and kinetic friction it's 0.615. How far does the object slide before it comes to rest? All right, so the picture looks like this. We have an object. It's sliding to the right. We have an initial speed of 10 meters per second. But there is friction, and there are no other forces horizontally. So, yeah, in fact, let's put that in. So friction, right, is going to go this way. And we have to decide, is it static or is it kinetic? In this case, it's very clear that the object, we already know it is sliding. It already has a speed. So this is kinetic friction. Okay. So, all right. So we can actually ignore the static friction number. That won't come into play. We'll just use the 0.615. All right. Now the rest of the forces, if I put my free body diagram on top of this, we have gravity going downward. We have normal force going upward. Okay, nothing is diagonal. That's nice. So in the vertical direction, we know that acceleration is 0. So Fn minus Fg equals may, but that's 0. We can put that in. Normal force minus mg equals 0. Normal force equals mg. And that equals 1.35 kilograms times 9.80, 13.2 newtons. It's 13.23 really. This is not a final answer, so when I use that, I will use the full number from my calculator. Now horizontally, we only have kinetic friction, so that's the net force horizontally. And that will equal my horizontal acceleration times m. Now we have a formula for kinetic friction. It is mu k Fn. Okay, so I can solve for ax. It is negative mu k Fn over m, and I have all three of those. So I put them into my calculator. I get negative 0.615 for mu k times my 13.2 or 13.23 newtons, divided by my mass of 1.35, and I get negative 6.0 meters per second squared. So that's my acceleration to the left, which makes sense because it's going to the right, but it's slowing down, so the acceleration is to the left. All right, so now and all these forces are constant. Friction is constant, gravity and normal force are constant, so this acceleration is constant. So I have a constant acceleration motion problem from here on out. I want to know how far it goes before it comes to rest. So I have my acceleration of negative 6.0. I know the initial speed is positive 10.0 meters per second, and my final moment is when it comes to rest, so my final velocity is 0. I am free to choose my initial position as 0, and I want to know how far the object has gone when it gets to a 0 speed, so that my xf is what I'm looking for. Time is not playing a role here. We don't have it. We aren't asked for it. So we look on our constant acceleration problem, constant acceleration formulas, and I think we want this one. We can put in a 0 here. We can put in a 0 here. So we get vi squared equals 2axf. We're solving for xf. So xf is vi squared over 2a. And I put everything in, so I get 10.0 squared divided by 2 times that negative 6.0. And I get negative 8.3. Whoops, I'm sorry. So actually, when I solved for this, there was a negative here. So there's a negative, it's negative vi squared over 2a, and a itself is negative, so the two negatives cancel. So it's actually positive 8.3 meters. So it will slide for 8.3 meters before it comes to a rest. Okay. Number 20. A 20 kilogram box initially at rest is on a ramp angled at 22 degrees to the horizontal. We have the two coefficients of static and kinetic friction. First question is, does the object slide down the ramp? And if so, what is the acceleration? Okay. So here we go. Here's our ramp. Here's our object. Free body diagram. We have gravity. We have normal force going this way. And we have friction going this way. We do not know if it's static or kinetic yet, right? All right. We put on our coordinate system, which is tilted. All right. This is our angle theta of 22 degrees. That means this is our angle theta of 22 degrees. Gravity is diagonal according to our tilted system. So we have to split it up into horizontal and vertical. This right here will be cosine, and this right here will be sine. Okay, so if we look at vertical, we have Fn going upward, and we have minus Fg cosine theta going downward, and this equals an acceleration that we know is 0. We know it's not going to accelerate in that direction. So the normal force is Fg cosine theta. If I bring that over to the other side, I can also sub in mg cosine theta. Okay, so there's your normal force. Horizontally, we have Fg sine theta going in the positive direction. Let's say to the right is the positive direction, minus friction equals ma. All right. So again, does the object slide down the ramp? Let's assume it doesn't and see if everything is a-okay. So if we put in a 0 here, right, then let's see what we have. We have mg sine theta minus F, friction force. So mg sine theta, 20 kilograms times 9.80 times the sine of 22 degrees. Let's get a number for that. 20 times 9.80 times sine of 22 degrees is 73.4 newtons minus F equals 0. We would get that the friction would have to be 73.4 newtons. The question we always ask ourselves is, if this, because this was under the assumption that it's not moving, so this would be static friction. But the question we have to ask ourselves is, can static friction be that big? We have a formula for the maximum that static friction can be. So the maximum static friction is μs times the normal force, which is, we've already figured out, is mg cosine theta. So let's figure out what that equals. μs is 0.43 times normal force, so times mg, so times 20 times 9.80 times the cosine of 22 degrees, and that is 78.1 newtons. So static friction can get up as far as 78.1 newtons. So it can be 73.4 newtons. That is less. So everything is a-okay over here. So the answer is, it does not slide. So, I mean, the acceleration is 0 because it's not sliding. And what is the magnitude of the frictional force? Well, we figured out that it's 73.4 because it's static friction. Oops. It's not the maximum. That's just what it could have gone up to. But this is what it actually is in this circumstance, 73.4. All right. Remember that if this number ended up being smaller than 73.4, that means it does slide, and we would have had to have backed up a few steps and not assumed that this was 0. So anything in green we sort of would have thrown in the trash and start over, because now we know it's kinetic friction because it does slide. But then we could use our formula for kinetic friction and figure everything out from there. Okay, but it turned out that it doesn't slide. All right, I will stop this video and continue in the next part.